Please join me in welcoming Sohini from Adobe.
Thank you. Okay. So good afternoon, everyone. Today we'll be talking about leveraging Osquery for DFIR at scale. And I'm Sohini, and I'm a security researcher at Adobe. So here's our agenda for today: rapid incident response, fast forensics, and proactive threat hunting. So why is a rapid or agile incident response plan so relevant in today's threat landscape? Because understanding the anatomy of an attack or how a compromise took place is one of the most daunting tasks that incident responders face, right? I mean, they have to put together pieces of the puzzle where the pieces might not even exist to begin with. But there's good news, because an attacker intruding a network or an infrastructure is bound to leave some changes somewhere. Maybe in the form of new user accounts, some suspicious process execution, etc., etc. Now, while pulling memory image from an infected endpoint and doing a full-blown forensic analysis with a tool like volatility is probably the most comprehensive way, but it's also very much time and resource intensive, right? So in today's talk, we'll try to explore that if you can adopt an alternate methodology by leveraging an agent that might be already running in the systems and see if it can fast-track our investigation. Now, there's a certain category of artifacts that are of primary interest to incident responders while doing a light disk analysis, like process execution, any associated network sockets, any new user accounts that the attacker might have created but forgot to delete on the way out, any suspicious file system changes, any weird kernel modules that were loaded, any evidence of persistence in the form of cron jobs or scheduled tasks, any evidence of code injection, any non-standard running services, and I can go on and on. So today we'll be talking about a couple of attack scenarios, and we'll primarily pivot on a couple of these artifacts, as in process execution and associated network sockets, and see if it can give us a head start into the investigation. Because when you're responding to a security incident, time is really the essence, right? And first, a little bit of background on Osquery. Why? Because Osquery is going to be our primary tool based on which we'll discuss if we can detect those attack scenarios. So the Osquery framework exposes the operating system in the form of SQL tables, wherein you can run SQL statements like select star from processes and grab interesting artifacts from your system. As you might be already aware, it's a popular open source project initially spearheaded by Facebook and backed by a robust open source community. There are many commercial vendors who are actively working on custom plugins and extensions to address many interesting use cases. The query language is generic across all platforms, so whether you're running Windows servers or Linux distros or macOS laptops in your environment, you can use the same generic query language to grab those interesting artifacts. It's a lightweight agent, it's non-intrusive, runs as read-only and on user mode. So let's look at a couple of Osquery statements. How does it look like? So select star from logged in users, select star from logon sessions, and as is intuitive enough from the output, it gives us information about the logged in user and the associated session information. Okay, one more. This time looking at the processes table, and instead of specifying a wildcard, we are mentioning our points of interest in the form of command line, process ID, and we are also grouping it by the top 10 most active processes that's running in this system. So I see there's 24 instances of SVC host running, which is probably okay. And I also do see that PowerShell is running in this system. So when I am investigating a potentially compromised Windows system, and if I see PowerShell running in there, I would be very curious. So let's keep looking further. So the real power of Osquery lies as we try writing more complex statements using join between the various tables. Like for example here, we are joining the process and the process open sockets table, and we are also mentioning a search criteria that give us the network connections that are not running on port 80 or port 443. So I'll take a quick pause here. Take a quick look at the output. Is there anything that stands right away to you? Any guesses? PowerShell. Yep. Yeah. So I see that PowerShell is running here, and that is making a weird outbound connection to a random IP address over port 444. I mean, it's not a random IP address because it's RSC 1918, because I'm just trying to emulate the scenario in the local lab environment. But you get the drift, right? So if at any point of time you see PowerShell is making such a random outbound connection, it might be, just might be, a Meterpreter reverse shell or a Cobalt Strike beacon that's running in your environment. Now you might arguably say, why would a smart attacker use something like a port 444? I mean, it's a red flag right away, right? I mean, he would rather use port 80 to gel into the regular traffic. Absolutely true. But here's our discussion on defense in depth comes across, where you would want to define various search criteria and detection logics to be able to track any scenarios. Okay. So before going into our attack scenarios, a quick high-level overview of our Osquery deployment architecture. So it's a classic client-server model where the Osquery agent enrolls or polls, the TLS endpoint responds with a query, and the Osquery agent replies with the results. So what is a TLS endpoint? So Collide Fleet is one such example of an open source Osquery manager or fleet manager per se, which serves both as a TLS endpoint as well as a UI. And this is how the portal looks like, where you can see a few of my systems have checked in, and you can also deploy your query packs via this portal and run it across your environment. So in a nutshell, the Osquery agent interacts with the fleet manager. And in addition, we are also sending over the logs to SIM for further analysis, say for proactive threat hunting or ad hoc artifact collection during an incident investigation. So without further ado, let's talk about our first attack scenario and on reverse shell. So here's how our attack unfolds. Say a phishing email has been delivered to your employees, which has a malicious link embedded into it. Now, unfortunately, an unsuspecting employee hasn't been able to detect the phishing email and has clicked on the malicious link. Hopefully, SOC team has been alerted and incident response kicks in. So here's what happens under the hood. On the right-hand side is the attacker box, and on the left-hand side is the victim machine. So the link over here is the malicious link that was delivered by the phishing email, which when clicked, some MSHTM magic happens, which maps to the MITRE attack technique T1170. A Meterpreter session is now open on the attacker box. Now, if this attack looked simple enough to you, I mean, let me reassure you, it's very popular among many APT groups. I mean, a top favorite among APT 32. So let's see, I mean, can we detect such a scenario? So by using such an Osquery statement, which looks into the process and process open sockets tables, I mean, a similar query that we discussed few slides back, it's possible to track the network connection that is just being made for the Meterpreter shell session to open. One more, this time leveraging regsvr, and this maps to the MITRE attack technique T1117, and this is also known as a squibbly-do kind of attack. So these are like proxy execution of malicious code that we are talking about. Again, a top favorite among APT 32, APT 19, Deep Panda, because it lets attackers evade detection, bypass application whitelisting, so on and so forth. So a Meterpreter session is open on the attacker box, and in addition to detecting the network connection, we also got a hang of the process that might be responsible for this compromise. Take a note of the process, it's PID 2188. So let's look into, I mean, what did this process do? What did it execute? And what better place than to look at the command line execution? Now, by running this particular Osquery statement, sure enough, we see a huge blob of malicious PowerShell script that just executed on the victim system. One more and the last of our reverse shell scenario on DLL injection. So this maps to the MITRE ATT&CK technique T1055. So meter-breeder session is open on the attacker box, and what the attacker did here is been able to drop a malicious DLL, msf.dll, into the downloads folder of the victim box. So we are able to track the network connection that was open because of the meter-breeder session. So far so good, but there's another interesting artifact that we notice here. Run DLL, which is a Windows system binary, is making an outbound connection to a random IP address over port 444. Why would that happen? Why would a system binary make a weird outbound connection? Let's keep looking further. So what place should we look at? Let's look at the process tree, right? I mean, which is the parent process which might have spawned run DLL and made it to make this outbound connection. Tracking the process tree and take a note of the process ID, we notice that it's notepad.exe and calc.exe which had spawned run DLL, which in turn made that outbound network connection. Red flag right away, right? Now notepad and calc are just like old copybook examples for demo purpose, but you get the drift once again. So what the attacker did over here, that the attacker was able to inject himself, as in inject the malicious DLL, into two apparently innocuous processes, notepad.exe and calc.exe, to evade detection. So another threat hunting 101 for you. If at any point of time you see a system binary like run DLL is making an outbound network connection, it's probably something that qualifies as an anomaly and needs further investigation on. So now that we got a hang of the process, which how the compromise might have taken place, let's see if we can drill down further on that particular process. So drilling down on process ID 3844, which was of calc.exe, we can list the the DLLs that is being loaded by this particular process. And sure enough, we see the malicious DLL, msf.dll, being loaded from the downloads folder. Another red flag right away. So now that we got a hang of the compromise, how it might have taken place, it's time to gather some more evidence on time on execution, and by leveraging the file table, it's possible to grab some file system metadata in the form of end time, modification time, C time, creation time, and birth time. The next of our attack scenarios on crypto mining. So there was a time when ransomware was a rage among the bad guys, and these days it's crypto mining. So here's how our attack unfolds over here. So our attacker has been able to grab some credentials which were hard-coded in source code and inadvertently committed to a GitHub repo. So the attacker authenticates with the stolen credentials. The attacker establishes alternate access by creating a new user account. The new user now installs and starts the miner, and the miner establishes connection to its pool. Hopefully SOC team has been alerted and incident response kicks in. So here's how if we deploy the Osquery statement, again leveraging the process and process open sockets query, from the Collide Fleet portal, it's possible to track the malicious process miner D that is making the suspicious network connection. But we are also sending over the logs to SIM for further analysis, and this is how the attack unfolds from a logging perspective chronologically. So here's exactly where the attacker had created a new user account, and this is the new user account which is CentOS user. And now the new user installs and starts running the miner. Now from a detection perspective, this is indeed the process that's running with no system package. And last but not the least, one of the telltale signs of a crypto mining kind of attack is a huge blob of DNS events where the miner is trying to reach out to its mining pool. Oops. So the next of our attack scenarios on container exploit attempts. So running containers, misconfigured containers like privileged containers, containers running without security profiles like AppArmor, containers running as root can lead to really vulnerable environments, right? So an attacker might be able to exploit an application vulnerability and compromise a certain container. And with enough elevated privileges, the attacker might be able to break out of the container and infect the underlying host kernel space. So from there on, it's comparatively simple for the attacker to make a lateral movement and grab a foothold into all the containers that sharing the same host kernel space. So scary situation, right? Scary, undesirable situation. Now, container forensics is challenging. One of the many reasons being how container is supposed to be. It's supposed to be short-lived, right? And container forensics is a whole new topic of discussion for a different day. But considering the time that we have left today, we have today for this discussion, let's see if we can proactively audit against the security flaws or security misconfigurations and be able to stop before any compromise takes place. So using Osquery, it's possible to query the Docker domain like a relational database, and we can run queries like this one, which audits for any privileged containers that might be running in your environment. One more on environment variables. So see if credentials are being put into your environment variables inadvertently, like keys or passwords, it's possible to audit against those scenarios and prevent sensitive information disclosure. One more, detecting containers that's running without any security profiles and containers running as root. And we can always write more complex statements like this one, which is proactively auditing for Docker open sockets. And here's where a quick note of outlier analysis, knowing your environment, knowing a baseline of known good behavior, right? So if we see a newly seen process that's running out of a certain socket, which is, say, also running out of a non-standard file path and making an unexpected outbound network connection reaching out to the internet, that is not necessarily malicious, but that just gives you an interesting subset of information to investigate further on, and you never know, you might get that all-important clue that might lead you to a compromised environment. But say what if none of this security flaws were detected and an attacker been able to compromise a container? Let's try it and think in the attacker footsteps. What would the attacker do next? Maybe he would try to pull further malicious code into the container to escalate privileges. He might want to install and start running a miner, and he might just use some tools like wget or curl to pull those malicious code. Now, knowing our runtime environment, what is the known good baseline would help here, because if wget or curl is something that is not expected to run in your container runtime environment, again qualifies for an anomaly right away, red flag right away. So by deploying such a Osquery statement, we might be able to track the command line execution and see if a wget was used to pull further malicious code. Now, as we approach towards the concluding part of this talk, I would want to reiterate this is not just limited to Osquery. All of whatever we had discussed, we can totally extrapolate and apply these scenarios into any commercial EDR tools that you might be running in your environment or any open source framework. So these are some of the references that I have found very useful. And just as an example, for example, the third one, the GitHub repo from Teoseller, is a very good resource which maps the MITRE attack techniques to Osquery statements. For example, svchost.exe is a system binary, Windows system binary, which should have services.exe as the parent process. Now, if you suddenly see that explorer.exe is spawning svchost.exe in your environment in a certain system, it is possibly a malicious payload that is just trying to evade detection or bypass application whitelisting. So just as an example, it is agnostic of tool, goes beyond Osquery, and can be applied to any detection logic that you might be using in your environment. So it's basically unleashing the power of open source, and hopefully together as a community we can work together and be a step ahead of the attackers. So I guess that's as much time that we had for today. I can take a couple of questions if we have time. If not, I'll be hanging here and we can have a quick chat if you want. Thank you.